In the last class, we have studied in detail about the definition and the construction of a Born-Haber's cycle for the formation of a ionic compound. Especially, we have discussed about the formation of sodium chloride, which is an ionic compound, and also we have studied few of the examples regarding the calculation of lattice energy with the help of a Born-Haber's cycle and a thermochemical equation given by Hess law. Sodium chloride and its formation is belonging to a monovalent compound. So today I am going to deal with the calculation of lattice energy of another ionic compound which is belonging to a divalent, particularly by taking an example of magnesium oxide. So today I am going to show the calculation of the formation of lattice energy of a divalent compound, particularly a magnesium oxide, with the help of a thermochemical equation. So coming to the lattice energy of magnesium oxide or any AB type of a divalent ionic solid. So here we have to calculate the lattice energy of magnesium oxide from the following data, where the sublimation energy of a solid magnesium is 136 kilojoules per mole. The ionization energy of magnesium, that is IE1, is equal to 738 kilojoules per mole, and the second ionization energy of magnesium, that is IE2, is equal to 1450 kilojoules per mole. Here we are going to consider the ionization energy of magnesium as first ionization energy and a second ionization energy, because for the formation of an ion from a metal, in magnesium, a metal atom, if we remove one electron, it forms M plus 1 cation. But here in magnesium, we have to make a magnesium plus 2 because it is a divalent atom. So here we have to consider the first ionization energy as well as second ionization energy of magnesium. Here first ionization energy is related with the energy required for the removal of one electron, and second ionization energy is related to the energy required to remove the second electron. So the ionization energy of magnesium IE, which involves the first ionization energy as well as second ionization energy. So the ionization energy of magnesium is equal to 738, that is IE1, plus 1450, that is IE2. In total, the ionization energy of magnesium is equal to 2188 kilojoules per mole. Coming to the another value, that is dissociation energy of oxygen, and it is equals to 498 kilojoules per mole, and the electron affinity of, coming to the electron affinity of oxygen, and it is equal to 355 kilojoules per mole, and the heat of changes of formation or the heat of formation during the formation of a magnesium oxide is equal to 411 kilojoules per mole. The heat of formation of magnesium oxide, that is delta HF, from the magnesium metal and a gaseous oxygen can be experimentally measured as the heat of formation of magnesium oxide, that is delta HF, from the magnesium metal and a gaseous oxygen can be experimentally measured as, that is Mg, which is in the form of a solid state, combines with half mole of oxygen in the form of a gaseous state to give magnesium oxide a solid, and it equals to 602 kilojoules per mole. The steps involved in the formation of magnesium oxide are: solid magnesium atom sublimizes to give a gaseous magnesium atom by absorbing certain amount of energy called as sublimation energy, and which is denoted by H sublimation or delta H sublimation. That is, a metal magnesium gives rise to a atomic gaseous magnesium. The sublimation energy, that is delta H sublimation, and it is equal to 136 kilojoules per mole. Coming to the second factor, the gaseous magnesium atom releases 2 electrons in 2 steps with the corresponding ionization energy. The second step involves the ionization of a gaseous magnesium atom into a gaseous magnesium ion. So here a gaseous magnesium atom loses an electron to form magnesium ion. Here magnesium loses 2 electrons to form Mg+2 ion in 2 steps. The first ionization energy of magnesium while losing 1 electron is indicated by delta H1, that is ionization energy for the removal of first electron is 738 kilojoules per mole, and in the second step Mg plus again loses 1 electron forming Mg+2 ion in the gaseous state, and the amount of energy required is called as second ionization energy, that is delta H2. Ionization energy is equal to 1450 kilojoules per mole. So energy of ionization of magnesium while converting a magnesium atom in the gaseous state to magnesium ion, that is Mg+2 in gaseous state, is equals to 2188 kilojoules per mole. Coming to the third step, that is the diatomic oxygen breaks down into individual atoms by the supply of a dissociation energy. Here diatomic oxygen breaks down into 2 individual atoms by absorbing a bond energy which is called as dissociation energy, such that each oxygen atom absorbs half of the bond energy of the oxygen molecule. That is, O2 by the supplying of a bond dissociation energy. A O2 molecule will be converted into 2 oxygen atoms. To dissociate one oxygen molecule into 2 oxygen atoms, the energy required is called as bond dissociation energy, and it is equal to 498 plus 249. So totally here the oxygen atom accepts 2 electrons to form oxide ion and releases energy equal to the 2 electron affinity, that is oxygen, a gaseous form, loses 1 electron to form a oxide minus 1 ion in a gaseous state. The electron affinity is indicated as delta H1 and it is equal to EA and it is equal to minus 142 kilojoules per mole. Similarly, the oxygen, by losing 1 more electron, the electron affinity is indicated as delta H2, that is again equals to EA, it is equal to plus 798 kilojoules per mole. The total energy released as electron affinity by the oxygen atom is delta H1 plus delta H2 and it is equal to electron affinity of oxygen and it is equal to 656 kilojoules per mole. Coming to the 5th step, that is gaseous magnesium ion and gaseous oxide ion combines to form a solid magnesium oxide, and this step involves the combination of both the gaseous ion, a magnesium in a gaseous state and a oxide ion in a gaseous state combines to form a magnesium oxide molecule in the solid state. So the energy released is equivalent to lattice energy, which can be represented as Mg plus 2, a magnesium ion in a gaseous state combines with oxide ion in gaseous state to form a magnesium oxide in a solid state. Whatever the energy releases is going to be called as lattice energy and it is to be calculated. According to the summation of enthalpy of all the process starting from to the formation of a final compound, whatever the net enthalpy changes gives the solid crystalline magnesium oxide from a magnesium and oxygen from their standard conditions. This should be equal to the experimentally measured enthalpy of formation of a solid magnesium oxide. So the enthalpies are the changes in the heat energy during the formation of a ionic compound is represented in the form of a cycle called as Born-Haber's cycle. So the following figure indicates the Born-Haber cycle for the formation of a magnesium oxide. Born-Haber's cycle for the formation of a magnesium oxide. from the constituent ions. Here, magnesium initially in the form of a solid state or in the form of a metallic condition combines with half mole of oxygen, that is, it combines with 1/2 O2, which is in the form of a gaseous state, forming a solid magnesium oxide. Whatever the heat energy changes takes place during the formation of a magnesium oxide is going to be indicated by delta HF, that is heat of formation. So here in the first step, the metallic magnesium is to be subjected to a sublimation. So when we supply certain amount of energy in the form of a sublimation energy to the metallic magnesium, it will be converted into a magnesium in the form of a gaseous state. So here a metallic magnesium, by the supply of sublimation energy, converted into a gaseous magnesium atom. So in the second step, the gaseous magnesium atom is again subjected to ionization. So for the ionization of a atomic magnesium in a gaseous state to a magnesium ion in a gaseous state, we have to supply certain amount of energy called as ionization energy. Here the ionization of a magnesium will take place in two different steps. In the first step, the magnesium atom, which is in the form of a gaseous state, loses one electron, and it is called as first ionization energy. Similarly, the magnesium, a gaseous ion which is formed by the loss of one electron, is again subjected to converted into a magnesium +2 ion. Here one more electron is removed from the magnesium, forming a magnesium +2 ion. So here energy required to remove one electron is called first ionization energy, and the energy required to remove the second electron from magnesium is called as second ionization energy. First ionization energy and second ionization energy itself is going to be called as a ionization energy of magnesium. So here a gaseous magnesium is converted into a ionic magnesium, that is Mg+2 ion is formed. Then coming to the third step regarding the dissociation of a gaseous oxygen molecule. To dissociate 1 mole of a gaseous oxygen into its atoms, the amount of energy is going to be called as a dissociation energy. To break down the bond between O2 molecule, the dissociation energy is required. So by the supplying of a dissociation energy to the gaseous oxygen molecule, it will be split up into 2 oxygen atoms in gaseous state. Then coming to the fourth step regarding the energy release when a oxygen atom is converted into a oxide ion. Here again the oxygen loses 2 electrons forming a oxide ion, and the energy released will be in 2 steps called as first electron affinity value and the second electron affinity value. Totally both the first EA and second Ea will give rise to the electron affinity value of oxygen while converting it into its oxide ion O-2. Then coming to the last step, the combination of a gaseous magnesium ion in a divalent condition Mg+2 combines with a oxygen which is so called as oxide ion having 2 minus charges. So here a positively charged magnesium and negatively charged oxide ion attracts each other. Due to the electrostatic force of attraction between cation and anion, a solid magnesium oxide is formed. So whatever the energy changes or energy released during the formation of a solid magnesium oxide with the gaseous ions is called as lattice energy, and that can be calculated as the heat of formation is equals to heat of sublimation plus heat of ionization plus heat of dissociation plus heat of electron affinity plus lattice energy, or according to the Hess law, the heat of formation is given by an equation that is delta HF, a sublimation energy, delta IE, a ionization energy, delta H, a dissociation energy, and delta EA, that is electron affinity value, plus lattice energy. So here substituting the values for lattice energy U, therefore U is equals to delta HF minus sublimation energy minus ionization energy minus dissociation energy and electron affinity value. By substituting the various values in the above equation, that is heat of formation is equal to plus 602 kilojoules per mole and sublimation energy minus of plus, that is minus 136 kilojoules per mole. Similarly, ionization energy, that is minus 2188, and that of minus of dissociation energy, that is minus 249, and that of EA, minus of EA is equal to 656 kilojoules per mole. On substituting the values, the lattice energy will occurs as minus of 2627 kilojoules per mole. Here, except lattice energy, all other enthalpies can be experimentally measured. Lattice energy of the magnesium oxide, a solid, from its constituent ions is minus 2627 kilojoules per mole. So today we have studied in detail about the calculation of a lattice energy of a bivalent compound, particularly a magnesium oxide, an ionic compound, with the help of a Born-Haber's cycle. And you have to calculate the lattice energy and the heat of formation of few more examples at your home. So in my next class I am going to deal with the factors influencing the formation of a ionic compound, and the importance of lattice energy and the solvation energy, as well as I am going to deal with the effect of lattice energy on solubility of a ionic compound.